Section 4.5 is optimization problems. And this is one of the most perhaps important uses of the derivatives of the derivative of a function when it comes to applications of calculus. It's also one of the more interesting uses. It's quite nice to be able to apply this to many different types of problems, either in mathematics or outside of mathematics, in engineering, physics, or finance or production. Really can show up all over the place. One of the difficulties is finding a function that actually has a derivative that's well defined. That could be the application problems that we struggle with. Of course, in our section, in our course, we're going to deal with functions that, of course, have a nice derivative, things that we're used to seeing, and finding the optimal values from those functions, from those value functions, either the minimum or the maximum, whatever the problem dictates. So a lot of us would just consider this to be word problems. Might be one way to see what this section's all about. And that, of course, is true, but specifically we're optimizing something, and that gives us this class of problems. So there's some general steps that we'll usually follow when we deal with a problem like this. Of course, this goes along with our related rate scenario. Understand the problem. Be sure you know what they're asking for and what the conditions are. If you can, draw a diagram for it. That always helps to lay out a word problem, right? Try to give a visualization to it. That should help you. And also, if somebody's going to grade your work, it'll give that person an idea of what you were thinking and how things got set up the way they did. In case something goes wrong, you can get some partial credit. Introduce notation. In other words, give unknown quantities variable names like X or Y or L and W for length and width. Try to be suggestive with those terms, right? P is perimeter, A is area, things like that. C is a cost, capital C, things like that. So substitute and simplify relations. So the quantity that needs to be optimized should be represented in terms of a single variable. Okay, so the quantity that needs to be optimized is usually a function of a variable or variables. We need that to be a single variable. So we're going to see this work. This happen time and again with the examples we work in this section. Two ways to simplify these relations are to look at the constraints or the relations of the problem and make substitutions from those constraints into the value function. And that's general, but we're going to see I'll point that out when I do it in the examples that we work on. Lastly, we find the extreme value or find the absolute extrema. Some cases, this could be a closed interval test. More often than not, it's a local min or a local max that we're looking for. Okay, how do we find those extrema? Well, it involves a first derivative and setting that first derivative equal to 0 to find the candidates for local extrema, and then checking whether or not they're local mins, maxes, whatever else. Oftentimes, we don't really bother to check if they're local mins or maxes in these problems because it'll turn out that the problem we're dealing with or the function we're dealing with will be automatically be able to determine whether or not it's got a local min or a local max or what. So let's get started on this. So this is a classic problem for optimization in calculus. So we have a farmer that has 3,600 feet of fencing and wants to fence off a rectangular field that borders a sheer cliff wall. Okay, so we have a sheer cliff wall here. I've started to draw the picture. Again, this is highly recommended if you don't already have a picture for it. So here's a sheer cliff wall. We only need fencing along these three sides of this rectangular area. Okay, she needs no fencing along the cliff, right? Okay, like it says along the wall. What are the dimensions that maximize the area of the field? So in other words, well, what lengths and widths should I choose this rectangle to be in order to have a maximum area? So obviously, some nice letters to choose here are capital A for area, right? So we gave that a name. These are widths. If this is a rectangular area, well, then each of these is the same. So they're both the length W, and this dimension on the bottom here is our length L. And if we want to talk about the area of this fence, we know that we're going to be talking about area equals W times L. It's one of the first things we could write down. We also know what are the dimensions that maximize the area. So we know that we want to maximize this function A equals W times L. And we'll almost always try to get this statement written down. We want to maximize which function subject to which relation, or constraint is another word here. We have to meet these conditions. That's a constraint, or we have to satisfy this relation. Okay. Maximize which function subject to which constraint. It's the way we want to think through this each time. Well, we already know the function right now. It's this one. We want to maximize the area. We have a constraint though. We only have so much fencing. She has 3,600 feet. We want to use all of it to maximize this area, right? So the perimeter of this fence needs to be 3,600. Well, that means 2 W's plus 1 L will give us the total perimeter and the total amount of fence that we'll use to do this. We know that this has to be 3,600 feet because that's the fencing we have to use to build the area. Of course, we want to use all of it to get the maximum amount of area. So there's no question about using any less than 3,600. We're going to use all 3,600 feet of it and try to maximize this area. Okay, so how do I find local extrema of a function A here of the variables W and L? Well, if this is called our value function, it's the one we want the optimal value from. In this case, we want a maximum from it. And really, if I could take the derivative of it with respect to one of the variables and set that equal to 0 and solve for it, then I could probably find the maximal value for this function. However, I have two variables here, and I really need one variable. I need this in terms of one variable. So what I look to is the second equation or relation that I have floating around here. I can solve for L in this equation, and I get L is equal to 3,600 minus 2 times W. Now I can substitute for this L the expression 3,600 minus 2W. That looks like is the following. Here's my L now. Now I see that this is fully a function of W, the area function of W. So area as a function of W is another way to put it. So now what I can do is take the derivative with respect to W of both sides of this. I get A prime of W on the left. That's just notational, really. And then on the right, well, perhaps I multiply this out a little further, or it looks like I actually, interestingly, just use the product rule. So the derivative of W is 1 times this function, and then plus W times the derivative of this function. Well, the derivative of the inner function there is -2. All right, so now I'll multiply this out and combine like terms. 3,600 minus 2W minus 2W. I get 3,600 minus 4W. What do I do with my derivative? I set it equal to 0. I'm looking for the critical numbers of this function. It's when the derivative is equal to 0. So 3,600 minus 4W equals 0. And now I have 4W equals 3,600. Solving for W, we get 900. So the width should be 900 feet, right? And it looks like the length should be, well, how do I find the length? I go back to the substitution formula that I came up with, and I can find my length by plugging in my width of 900. So 3,600 minus 2 times 900, and that's 1,800 is the length. So it looks like the dimensions that maximize this are 900 feet and 1,800 feet. What is our maximum area? Well, that's just a matter of multiplying those two numbers together, or whatever your function might be, plugging those two values back into it to determine what your maximum is. So the maximum area is the maximum value is the area that you get. The maximal values are the dimensions you use to obtain that maximum area. So there we are. It might be interesting to note, you can compare this to a couple other pairings of values here. So 900 feet and 1,800 feet. Of course, you add up two of these to this one and you get 3,600 total, and that matches the total perimeter. And you can multiply them together to get what you get there. I think you'll get something like, well, it'll be a pretty large number, but nonetheless, you can find that value and then maybe compare it to some other options. You could have used perhaps 0 feet for your width and then 3,600 feet for your perimeter. Well, 0 times 3,600 is an area of 0. You've done better than that case. That's the smallest case, actually. So there you are. Okay, so other arrangements might work out as well too. You could say, well, let's try 200, 200, and then that's 400 less, so 3,200 here. What's 3,200 times 200? You could see that that's actually a lesser area than this one. And that's just spot checking. That's not proving that you found it doesn't prove that this thing is maximal, but it just helps you check to realize that, yeah, this seems to be a larger area than any other choices. Okay, so that was it. That was one iteration of these problems. So these are a little bit less applied. We have a couple examples here that have less application, more mathematical background. So they might seem a little cleaner, and maybe some students prefer these. They can be a little tricky, I think, though. So this problem asks us to find two numbers whose difference is 10 and whose product is a minimum. So two numbers whose difference is 10 and whose product is a minimum. We want to minimize a product. We want to keep that in mind. So the constraint is the fact that these two numbers need to have a difference of 10. So in order to represent two numbers, I'll just come up with these two letters, A and B. A and B are my two numbers that I'm interested in. These two numbers need to meet this condition or this constraint, right? A minus B needs to be 10. Their difference needs to be 10. The next thing I might write down, I want to minimize. I want to find their minimal product. So the value function here is that product, A times B. So I want to find a minimum for this function, but I have two variables. I need to write it in terms of a single variable. So maybe I go up here and solve for A. I add B to both sides, and I'm able to write down A as 10 plus B. With that in hand, I can change my value function to now be V equals 10 plus B to replace A times B. Now I have a value function that's completely in terms of one variable. That's the variable B here. And, well, I've written it now as 10B plus B squared. And I can now look at it and say, well, I want to know what my maximum of this function is, or minimum rather, sorry, minimum. So I'll take the derivative of it and set it equal to 0. Well, the derivative of this function is 10 plus 2b, as we see here. And then set that equal to 0, so 10 plus 2b equals 0. Well, 2b is equal to negative 10. B is equal to negative 5. So we have one of the values, and then to find the other value, I plug it in up here, and 10 minus 5 is 5, so A is equal to positive 5. Okay, so now what I've found are these two numbers that satisfy this. I have 5 and negative 5 satisfy this equation. This is kind of one of those math puzzles. Find two numbers whose difference is 10 and whose product is a minimum. It really takes a lot of the mystery out of those types of puzzles now, because we have a very direct way to represent the constraint, write down the value function, substitute the constraint into the value function, and then optimize the value function to find the pair of numbers that do that. And if you want, you could check a couple other values. Two numbers whose difference is 10. There are infinitely many of those. So you could try something like 10 and 0. 10 minus 0. What's the product of 10 and 0? Well, 10 and 0 has a product of 0. Well, that's not less than 5 and negative 5, which have a product of negative 25. So there, just spot check to see that, sure, it looks like my value is lesser than any other ones I could come up with. Yeah, so you don't typically need to do that, but it's worthwhile to think about that as an option. Okay, so getting a little bit more complicated, let's look down at this second example. What's the minimum vertical difference between the parabolas y equals x squared plus 1 and y equals x minus x squared? Minimum vertical difference between each of these parabolas. It really helps to try to sketch these parabolas. X squared plus 1 is easy to sketch, right? It's shifted up by 1, but its vertex is on the y-axis. X minus x squared, well, that's x times 1 minus x. The zeros of this parabola are 0 and 1. The roots of it are 0 and 1, as marked here in the sketch. It opens downward because it has a negative x squared. And that's about all we need to do, right? Just to get a rough idea of what these two things look like. Now, Of course, somewhere in here, there's a minimum vertical distance or difference between these two things, right? It looks like the one I picked out and sketched in there is probably more or less it. But in order to find this thing, we need to use some calculus, right? We don't exactly know where that is. So what we'll do is we'll talk about the value function. The value function is the difference. We want to find the minimum vertical difference between these two parabolas. Well, the vertical difference between two parabolas or two functions is the difference of those two functions. So our value function is simply the upper parabola minus the lower parabola. Here's the upper one, here's the lower one. So there we have it. Upper and lower, and then simplify this expression. We combine like terms to get 2x squared minus x plus 1. Now we want to optimize this. What's really nice about this value function is all of my variables are x. So I don't have to do any work. I don't have to substitute any relation or anything like that. That's all already taken care of, right? Or it's at least not just work we don't have to do this time. So v prime of 0, the derivative of this, set it equal to 0. That's 4x minus 1, right, equals 0. When I solve for x, I get x equals 1/4. So we have a minimum at the x value of 1/4. So let's be careful about what they're asking for, though. They don't ask us where the minimum vertical difference occurs. That's at x equals 1/4, right? They ask us what the minimum difference is. What is the minimum difference? That's where we need to know the value of our value function, right? Because that is, in fact, the difference between these two. It has a minimum when x equals 1/4, but its minimum value is when we plug 1/4 into that function itself. So here we do that down below. V of 1/4, x squared minus 1. Oh, sorry, I used this expression just because it's a little faster, so that's fine. 2x squared minus x plus 1. X is 1/4 in all cases. And when we're done simplifying that, we get 7/8. So there we are. That's the vertical difference. That's the minimum vertical difference. We found where to come up with it, and then we found what it was. Okay, so keep that in mind. They might ask you, what is the minimum or maximum in one of these cases? All right, so let's just to compare that to our first problem. What did they ask for? What are the dimensions that maximize the area of the field? They didn't ask what is the maximum area of the field. So keep that in mind. That's why we were able to stop at just the dimensions that we solved for. We didn't have to plug them back into the area function unless they asked what is the maximum area. So let's move on to another one. Find the point on the line y equals 2x plus 3 that is closest to the origin. These are interesting little, again, math puzzles, right? What's the point on this line? In other words, what's the xy value on this line, y equals 2x plus 3, that minimizes the distance to the origin, that's closest to the origin? So we want to minimize the distance of 2 points in the plane. One of those points is 0, 0. The other point is xy. We don't know what those values are. We're trying to find them. So what's the distance between the point xy and 0, 0? Remember the distance formula. The distance formula between xy and 0, 0 is given by this formula here. It's the square root of x minus the x coordinate here, plus quantity squared, plus y minus 0 squared, square root of all that. Okay, so this is the thing we're trying to minimize. We want to find the minimum distance. And, well, the problem is this thing is defined in terms of two variables right now. X squared and y squared are in there. So we need that to be in terms of either x or y. But what we're doing is this point is on this line, so it satisfies this equation. This is a constraint, right? It's got to be a point on this line. So it's got to satisfy the equation of this line. So that's subject to y equals 2x plus 3, or subject to the relation here. So we're trying to minimize the distance, this function, with respect to the relation y equals 2x plus 3. Now we have everything we need. We have a value function, that's our distance, and then we have a relation, that's the equation of the line. So the distance now, we know that y is equal to 2x plus 3. So wherever I had a y up here in the distance function, I'll replace it with 2x plus 3. Now, of course, x minus 0 is just a quantity squared is just x squared, and y minus 0 quantity squared is just y squared, but y has been substituted for 2x plus 3. So we need to square this binomial and then combine like terms. Of course, all of this is taken to the 1/2 power to match the square root of the distance formula. So let's simplify in here first. We expand this term to get this trinomial. And when we combine all these values together, we see that our distance function is now given as follows: 5x squared plus 12x plus 9 to the 1/2 power. Now we take the derivative of our value function d and set it equal to 0. That's a chain rule. 1/2 comes down times the inside, right, to the power of negative 1/2. So that's our power rule. And now our chain rule step is times the derivative of the inner function. Well, 5x squared has derivative 10x, 12x has derivative 12, 9 has derivative 0. And then we set this equal to 0 because we set the derivative equal to 0. And we try to solve for x from here. Now notice this is to a negative 1/2 power, so I can write this as 10x plus 12 over, well, and this is a 1/2, so over 2, and then all this to the positive 1/2 power. Once these terms collect together, just a little bit of algebra brings us here. Now I want to solve this being equal to 0. Well, the denominator cannot make this expression 0, only the numerator can. So I'm only looking for 10x plus 12 equals 0. In that case, I'm looking for 10x equals negative 12, subtracting from both sides. Divide by 10, I get x is negative 12 over 10, which is negative 6 over 5. Don't get too excited yet. What are they asking for? We've found our minimal value of x. We found the x value that will minimize the distance. Do they want to know that, or do they want to know what the distance is? They say, find the point on the line that is closest to the origin. Perfect. Okay, so they don't want the distance. They want to know what the point is. What we just found was the x value for that point. We now know that x is negative 6/5, and that's the point that's closest to, or that's the x value of that point. Okay, what's the y value? Well, I know it's on this line, so I'll plug in negative 6/5 into this line, and looks like I do that down here. And we have, it's like the end result of that is 3/5. So the point negative 6/5, 3/5 is the point on the line that's closest to the origin. It minimizes the distance from the line to the origin of any point that's on the line. So that's a pretty interesting and powerful tool, right? Guessing which point this is that's closest to the origin around here, or and on this line, it would be tough work without a tool like this. So it'd be a lot of guesswork, maybe some tricky either geometry, maybe even trigonometry, right? Because we're talking about a right triangle would be our distance from there. Nonetheless, this works out pretty well as is. One option that we have when dealing with a distance function, notice we use the whole distance function here. The square root function happens to be a monotonic function. It's an increasing function. It only ever increases. So it preserves minima and maxima. So instead of working with the distance function with the square root, we could optimize, we'll call it capital D, the squared distance function. And what that does is it gets rid of this radical, and we can actually optimize with that instead. So if we did it that way, we optimize D as a function of x, capital D, right? Which is the little distance, or the distance function squared. The only thing that's not here is the radical on the outside. There's no 1/2 power here anymore. And if you do this, you'll see that you end up with the same value. It's actually easier work too. The derivative of this function is 2x plus 2 times 2x plus 3. This 2 is the chain rule. It's the derivative of 2x plus 3. When you put all that together, you get another 10x plus 12. You're setting this equal to 0. When you solve for that, you get negative 6/5. This is a faster, easier way to do it, and it's probably less error prone. But yeah, it's a nice trick for dealing with the distance function. You don't have to use the one with the radical. You could just use the inner function, call it capital D, and then take capital D prime equals 0, solve for x or y, whatever it is you might be reducing to as a single variable. Okay, moving on. Another more or less classic problem here in Calc 1. So a box with a square base and open top must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used to construct the box. Okay, so we need to meet a certain volume. That's our constraint, right? And then we need to minimize the amount of material used to construct the box. Well, the material makes up an area around this box, right? It's got an open top, so it only has the 4 faces on the sides and then a bottom face. So 5 faces on this box, so 5 surfaces are the areas that the surfaces we're trying to keep the smallest by maintaining the box at this volume. Okay, so I sketch the picture real quick, right? I draw more or less a rectangular solid, right? So serving as a box. I've shaded it to look like it's got an open top. It's more or less, that's maybe not so important, but nonetheless, we see that. Now it has a square base. So instead of calling this L, W, and then the height H, since these two edges on the base have to be the same, I call them both W. So I've already simplified that right away. So try to do that if you can. If not, you can just make that a step. Now H is the height and W by W. The volume of this box is W times H, length times width times height, or in this case, W squared H, thanks to the square base. So now we've got, what is this? That's our constraint function, right? We need the volume to be 32,000 cubic centimeters. So we need this function to be equal to 32,000 cubic centimeters, or just 32,000. There are no other units in this problem. Whenever we solve for W or H, we know that that will be in centimeters because they'll inherit it from this given unit here. So that's a constraint, right? Any equation that is equal to a number in this situation is our relation or our constraint. What's our value function? We need to minimize the material, the area, the combined or the summed area of all these faces. Well, notice we have a W times H face, that's this area, another W times H, another W times H, and a fourth W times H, plus the bottom face has an area of W times W. So there we have it put together in the picture. The area, we're trying to minimize this area too, is A equals 4 times WH. Those are the 4 faces on the side. And plus W squared. That's the area of the base. Remember, there's no top, so there's no area to minimize there. Okay, so I want to find the minimum of this function. Problem is, it's in terms of 2 variables. Otherwise, I would go right at it and say, take the derivative of A and set it equal to 0 and solve for the variable. Well, in order to get out of this mess, I come back up to my constraint or my relation and say, well, let's solve for H in this. When I do so, I get H equals 32,000 over W squared, coming from there. And now I have a substitution for H that involves W. So I'll do that. And that's the next line below. 4W times H, this substitution here, plus W squared. Okay, now I simplify, and then I'll take the derivative once I'm happy with my simplification. These W's cancel to a W to the negative 1 power. 4 times 32,000 is 128,000. And then plus W squared. Nothing major is going on over there to the side. So I've got 128,000 W to the negative 1 plus W squared. I'm going to take the derivative. It's all one variable now, W. I'll take the derivative with respect to W and set it equal to 0. So here's where that work happens. Here's my derivative, right? Just straight power rules. Here's me setting it equal to 0. And then maybe to simplify this, let's multiply all sides by W squared. That gets rid of this W to the negative 2. We're just a constant here. And 2W times W squared is 2W cubed. All of this equals 0 still. And now we're just going to solve for W cubed and then W. So here's this line adding 128,000 to both sides. W cubed is now 128,000 over 2, which is 64,000. And the cubed root of 64,000 turns out to be 40. Not plus or minus, but 40, right? This is an odd root. So it's a odd root of a positive number is positive number, right? So W is 40. So that's one of the dimensions. And again, let's double check. What do they want? They want us to find the dimensions of the box that minimize the amount of material used to construct the box. Okay, to minimize here. Find the dimension. So we already have one dimension, it's W. To find our last dimension, we'll plug W into this relation for H and solve for H. So H is 32,000 divided by W squared, or 40 squared, which is 1,600. And that comes out to 20. So H is 20. So it looks like we have the dimensions will be a height of 20 centimeters, a width of 40 centimeters, and the other width of 40 centimeters. Remember, we need 3 dimensions here. W gets used twice because it's the square base length. Right, so that bottom rectangle of the box is a square, and it's 40 by 40 because we found W to be 40, right? And then what's left for the height is that 20 centimeters. One thing you might check is that if you multiply these 3 things together, that you get the volume you expect to get. We should get 32,000 out of that. So that's one check. And yeah, we could check the area of it compared to other boxes, but that's a lot of work. It's not at all necessary to go checking to confirm that this is a maximum or a minimum. Typically, the way these problems work out is that, at least from the textbook and any Calc 1 situation, is that once you find these local max or local mins, they are in fact what you think they are, and you don't have to get too carried away with proving that they're maximums or minimums. So there are a couple further examples. I'll leave these for students to work on. These are sort of the fun little math puzzles. The sum of 2 positive numbers is 16. What's the smallest possible value of the sum of their squares? So find the constraint, determine what they're looking for. The smallest, we're looking for a minimum, right? The minimum of the sum of their squares. What's the minimum vertical distance between the line y equals 2x and the parabola y equals x squared plus 3? We've done a problem similar to that. So these are great exercises to get started in this section. And overall, to get good at these problems, just like anything else, it's just a bunch of practice. So good luck with that.